Hey there, Calc 2 folks, back here with another lecture for you leading into test number 3 material. We have wrapped up looking at infinite series in the previous chapter. Now you got to be kidding me. Do I have... hold on here. Let me fix this. I got wrong chapter titles up here. Well, we just finished chapter 10 material, so we are moving on to chapter 11. Where we're going to be looking at power series, and particularly we're going to start here in section 11.1, Taylor Polynomials. So let me fix that like I just did here. Now, again, we've just finished our study of infinite series, and as we had highlighted at the beginning of that study, some of what we were preparing for was this chapter 11 material where we're going to spend a little time studying what we call power series. All right? And particularly in our study of power series, we're going to spend a little bit of time, and a lot of the chapter focuses in on the case of what we know as a Taylor series, all right, which is going to be a special case of a power series, right? To begin that study into power series and to begin our study into what we call Taylor series, we look at a simpler case of a Taylor series, what we might think of as being a finite case for a Taylor series, and that being what we refer to as a Taylor polynomial, right? And that is where we do begin this section 11.1 material. Chapter 11 material is looking at what we call Taylor polynomials. Now, to begin facilitating this idea known as a Taylor polynomial, what I open with is what I call linear, quadratic, and cubic approximations of a function. All right? We do have calculus methods for developing what we call approximations for the values of a function, right? And what we're going to see develop in this first bit to this set of notes is what we call the linear, quadratic, and cubic approximations of a function. Right, and this is part of calculus. Calculus is not only a study of limits, but it's a study of using limits to help you to do some very complex calculations at times. And what we're going to look at here is using limits, right, to help us develop what we might call complex transcendental calculations. Right? How do we go about calculating something like we see down here below, right? We might consider the function for the moment e to the x, right? The natural number e raised to the power of x, right? The natural exponential function, right? Now we do know a few of these transcendentals without a calculator. For instance, we know f of 0, right, is equal to e to the 0, which is equal to the value of 1, right, in value. If we were to take and substitute 0 in for x into this function and evaluate e at the value of 0, we do note that any value raised to the 0 power will equal the value of 1, right? That's rather readily known. And we also know through a study of limits what the true value of e is. E is experiencing is this description of constant growth, right? It's a constant growth rate, where e is about 2.718 if we go out to 3 decimal places. All right? And in fact, that value itself required a little limit in its interpretation, right? But what about thinking about a value like we see down below here? What about the value f at 0.1, or what would be e to the 0.1 value? Or, what would be this value of e? Now, on a calculator, our calculator will do this calculation for us most certainly. It'll give us 1.10517091808. But I point out, how does our calculator know that? Right? Or how did mathematicians calculate e to the 0.1 value 50 years ago when calculators that we have today were the size of rooms, right? The size of whole floors on big buildings, right? To do these calculations. How do we do these calculations 100 years ago, right? At the beginning of the electronic age, right? We had to rely on some other methods. right? And what is programmed actually into our calculator to develop these calculations are some of the methods we see develop here in this chapter, right? So let's consider, right, that here as we move forward, right? Certainly we do have calculators that are going to do a lot of these calculations for us, right, nowadays. But let's think about how those calculators are programmed to do those calculations. Or let's think about what is actually going on in the background, for instance, in these calculations on our calculators, right? Well, in this section, we will learn how to develop what are called Taylor polynomials, right, to begin approximating what are known as these transcendental values. This value, e to the 0.1 value, we might think of as a transcendental value. To begin just mentally wrapping our brains around what that would be in value does require some higher level thought, right? Where we could use some limit techniques, some calculus, right, to help us with that higher level thought, right? So let's bring that into picture here. We are going to open up with this being our kind of our bigger picture. And let's look at some linear, quadratic, and cubic approximations of e to the x, right, to help us give us this value, e to the 0.1 value. All right. To begin, we could, for example, right, we could consider or develop, right, a linear approximation of f of x equal to e to the x at values of x near 0, right? You notice 0.1 is awful close to this value is 0, where we know e to the 0 power is certainly the value of 1, right? By determining what we call the equation of the line, I really should say the equation of the line, not passing, but tangent to our function f of x e to the x at the value of x equal to 0. We may have seen this topic presented back at back in Calc 1 material, where we were looking at application of the derivative, chapter 4-ish, where we were looking at developing linear approximations of a function, right? There was a approximation technique that involved building the equation of the line tangent to a function at a particular point, and that's what we're considering here. Well, in general, that linear approximation of our function might be given by this value we're going to call t sub 1 of x. It's going to be this function that we're just going to denote as function t sub 1, right? That describes this linear approximation of f of x near our value of x equal to a. And in general, that linear approximation is going to be given by this calculation here. It is going to be the value of our function f that we're approximating at that value we are near in our approximation, right? And that's going to be added to the value of our function's first derivative at that value we are near, right? That value of a, times this quantity x minus a. Or keep in mind x is the independent variable in our what's going to be approximation function, this linear approximation function. And again, a is this value that we're going to be near. All right. This formula, a formula very similar to it, was presented back in chapter 1 material. I believe what we called it back in chapter 1, I think we called it function L of x, right back in that chapter. We're just going to now denote that function L of x as t sub 1 of x. All right. If we consider developing that for our example here, I bring that up into view. All right. So folks, if we look at our particular case, right, note for the case of f of x equal e to the x, right, we might say here near x equal to 0, right? This being our value of a, right, in the calculation above, f of x equaling e to the x in our calculation up above. Since our first derivative of e to the x is also just e to the x, the slope of the line tangent to f at x equal to 0, right, passing through the coordinate 0, 1, right, has a slope of 1, right? So t sub 1 of x, the linear approximation of f near x equal to 0, is actually given by this calculation right here. This is the formula set up above. I did rearrange these two terms, right? Here we have f prime of a, we know that's 1. Here we have the quantity x minus a, that's x minus 0, right? And that is added to f of a, which is back here at the end, plus 1, which when simplified gives me this linear equation x plus 1, right? The linear function t sub 1 of x equal to x plus 1 is a linear approximation of the function f of x equal to e to the x near the value of x equal to 0. Right? And as a linear approximation of that function near x equal to 0, we can begin using it to approximate, for instance, the value e to the 0.1 value. Right? If we consider approximating then f at 0.1, t sub 1 at 0.1 would be a good approximate to begin with, and it tells us that value would be about 1.1 in value. Notice making x 0.1 inside this function, right, substitutes 0.1 in here to this linear function x plus 1 for x, and that is just 0.1 plus 1. That is 1.1 in value. All right? Where when we go back now and we compare that to our function f at 0.1, right? F at 0.1 is 1.1, what we've gotten in our approximation, times this quantity, well, I should say with these additional decimals added on to it. But notice nonetheless, if we were to round up, to the nearest 2 decimal places, to the nearest 10th, 100th value, e would round to 1.11, t would be 1.10. We're off by only about 100th in value in our approximation, give or take a few extra decimals. All right? This is pretty accurate. In fact, we could say we're accurate out to the nearest 10th of a decimal with this first approximation. All right? If we compare the graphs, here we do have the graphs of these two functions. All right? Note the following illustration of their graphs. Certainly the curved graph is our function e to the x, and we're not looking at all of it. We're just really interested in being close to this value of x equal to 0. Right? So at 0, we do know that it would be passing through at the value of 1, right? And what we've developed in t sub 1 is this line tangent to the curve at that point. And note that line tangent to the curve at that point, right, gives us pretty good approximations of that function close to the value of x equal to 0. If we notice where 0.1 is at, right? 0.5 is right here, so these are about tenths in value, right? That's 0.4, 0.3, 0.2, 0.1. It's right here along the x-axis. It's the first tick mark to the right of 0 on our x-axis. It's right about here in my graph. And we can see that right about there, the line, the linear function, is very, very close to the function f of x itself, e to the x. Right? Note for values of x near 0, the value of t sub 1 of x yields values very close to e to the x. Right? However, the further the further x differs from 0, the more we go from left or right of 0, right? If we were all the way out here at, for instance, an x of 1.0, right, the approximation is going to lose precision, right? We can see as we deviate from 0 along our x-axis, the greater the vertical distance we gain between our two functions. The worse, or the functions whose approximate is represented by this line decreases in precision when compared to this curve. All right? However, we can use a little bit of calculus to develop an approximation that maintains a little closer precision near this value of x equal to 0 in our function f of x equals e to the x. What we can actually go on to develop is what we call a quadratic or parabolic approximation of our function. All right? That is going to give us a little bit more precision. Now let's state in general here how we're going to find this result. And it is very similar to how we found the linear approximation, right? To begin with, we'll note, in general, a quadratic or parabolic approximation of a function near x equal to a, we'll call it t sub 2 of x, will be a function where what's unique about it is that its first derivative at the value of a will equal f prime of a, and that is what we see is true up here in the linear approximation. What's unique about t sub 1 of x and f of x is that their first derivatives at this location on the curve or the line are both the same. Well, that's going to continue to be true, right, in our quadratic approximation, this parabolic approximation, but we're going to also add to that this condition, right? This condition being that t's second derivative at the value of a, and really I should maybe point out, we're talking about t sub 2 here. This first approximation is equal to that, and t sub 2 here's second approximation at the value of a is equal to the second derivative of f at a. Right? What we end up developing is an approximation that's given down below here, where what's unique about this approximation is not only is the slope of the line equivalent to the slope at this point on our curve, what we're going to see is the concavity of the parabola is going to match the concavity of the curve at this point. Right? We will see not only a slope match up, but we will see a concavity match up. Remember, in second derivatives of a function describe concavity of a function, going back to application of differentiation back in Calculus 1, Chapter 4 material in our book. Right? And in general, the way we develop t sub 2 of x, it is, you'll notice, these first two terms, where those first two terms are what we saw describing the linear approximation t sub 1 of x, where t sub 1 of x now, right, these first two terms being t sub 1 of x, we're just going to add on this additional term. Now, what this additional term is, it is, first of all, going to be the second derivative of function f, the function we're trying to approximate, at this value of x equal to a that we're near. That being then times by this quantity squared, where this quantity involves the independent variable x. X is the independent variable in our function, just like this x was back in our linear case. And again, a is the value we're going to be near in our approximation. And those two factors are multiplied by this quantity 1 over 2 factorial. Right? Or divided by just the value of 2 factorial. Now keep in mind, what is 2 factorial? 2 factorial is just starting at the number of 2 and multiplying it by the next number less than it. It would be 2 times 1. In mathematical interpretation of factorial, or if we think about having a k factorial is really the number of ways to arrange k items. So 2 factorial is asking us how many ways can we arrange 2 items, and there are 2 ways to arrange 2 items. If you have a and b, you can have them arranged as a and b, or you can have them arranged as b and a. There are 2 ways to arrange those 2 items. And the way we calculate, again, a factorial is we take the number given in the factorial and multiply it by every integer less than it, every whole number less than it, down until we get to the very last whole number of 1. For 2 factorial, that's just 2 times 1. For 3 factorial, that would be 3 times 2 times 1. For 4 factorial, that would be 4 times 3 times 2 times 1. And what we get in the case of that number is just the number of ways we could arrange that number in the factorial. All right? But here we go back to our quadratic approximation. It is nothing more than our linear approximation with this additional term added to it. All right? If we develop that specific to our case, right? So for f of x equal to e to the x, near x equal to 0, since our first derivative of f is equal to e to the x, and our second derivative of f is equal to e to the x, this quadratic approximation, this parabolic approximation, is going to start off looking like it did in the linear case, with f at 0 plus f prime at 0 times x minus 0. But we're going to now add on this additional term, where this additional term is going to be 1 over 2 factorial, which we know is just 1 over 2, 1/2, times f's second derivative at 0. Well, taking f's second derivative at 0 is just going to be, again, e to the 0, which we know is 1 in value. So this first, the factor times this 1 over 2 factorial here in the middle is just 1 times x minus 0 to the second power. Well, that's just x squared. And this third term that we add on is 1/2 x squared. Or in simplest forms is given by this quantity here, 1 plus x plus 1/2 x squared. And what you notice we have here, folks, is a quadratic description of this approximation. This is what we think of as a polynomial description, right? Notice it does involve that linear description, 1 plus x, which is also a polynomial description. But now we've added this extra term that has made it into a quadratic, a parabola in its approximation. If we actually use this to approximate values of e of x near 0, we might consider approximating, right, f at 0.1, which would be e to the 0.1, using t sub 2 at 0.1, right? Now, 0.1, do notice that is just 1/10 in value, so I do kind of set this up to begin with some fractions to make the math a little easier to see happen here, right? This is going to be just 1 plus x, which is 1/10, plus 1/2 times 1/10 squared, quantity squared. Now, 1/10 quantity squared is 1/100th. Times 1/2 is 1/200th. So this third term we're adding on is 1/200th in value. Now converting that back to a decimal is just 0.005. Right? That is 5 1,000ths, which is equivalent to 1/200th in value. So this this quadratic approximation is just 1 plus 0.1 plus 0.005, which gives us 1.105 in value. And notice that is accurate in approximating e to the 0 power to the nearest thousandth. Right? That is actually accurate out to the nearest thousandth. If we go back up to the true value of e again, and I just copy and paste this down here for the moment, the true value of e is certainly irrational, folks. E to the 0.1 in value. But if we bring down its comparison here, and I'm just going to put this in momentarily, right? E to the 0.1 in our calculator gives us approximately this in value. And you can see with just a little bit of calculus, we have that approximation accurate out to the nearest thousandth. In fact, if you take a note, if we would round this up, right? Round this 7, use the 7 around the nearest 10,000th, right? Round our e to the 0.1 to the nearest 10,000th here. This would be 1.1052. We have 1.105. There's really only a difference of these two of about 2/10,000th in value, which is actually extremely accurate. Right? It's starting to get extremely accurate in its precision. And notice, folks, we were able to basically calculate that almost mentally. right? Plugging in 1/10 here and plugging in 1/10 here, our interpretation of 0.1 as a fraction, we could do all of this math mentally, right? 1 plus 0.1 plus 0.005, well, that's 1.105 in value, right? Evaluating polynomials is not a tricky procedure. Evaluating this quadratic function, a polynomial function, at any given value of x isn't really a transcendental procedure. To evaluate polynomials involves just our 4 basic mathematical operations: addition, subtraction, multiplication, and perhaps at times division. That's all that we're really doing here, is we're doing some addition or subtraction at times. We're doing some multiplying at times, like taking x times x, and then at times doing a little division, like multiplying by this fraction. All stuff we can do with paper and pencil methods and a little rigor, if need be, if we can't necessarily handle it mentally. But there are even going to be cases where we can develop these calculations with a mental technique, right? A mental calculation, all right? So notice we do get this value approximated out to the nearest thousand, accurate out to the nearest thousandth. Let me remove that just to keep the notes concise here. All right. Applying the approximation is precise in approximating f of 0.1 to the nearest thousandth of a decimal. All right. If we actually take note of their graphs, right, we can see that increase in precision. If actually I bring down this graph just to compare the two side by side, right? The linear graph is the first graph. The quadratic approximation is what we developed here, and we can see that notice the scale has not changed in these graphs, folks, right? The blue curve, or the curve that we see here, and if you have this in black and white, you might not be able to see it, but we do see our EX curve, the exponential curve, still here in black, right? It's the curve that is the same in each picture, whereas now our parabolic curve is this curve here. And notice it does appear to be a much better approximation for values of our function e to the x near 0. It has a lot more precision for a lot longer, for a kind of a wider interval around this value of 0. It does a pretty good job. It does a much better job than this first case. Right? And notice it is just a parabola. It is here just a portion of a parabola. If I was to look at the whole parabola, we might see the whole parabola moving through the picture like this, but we're really only focused on this region. And keep in mind what's unique about that parabola. What's unique about that parabola is, first of all, at this point I'm pointing to it with my arrow here, the slope of both of these graphs are the same. And just like in this picture, the slope of both of these graphs are the same. But what we've added to make this graph a little more precise is we've made its concavity at this point match the concavity of the function e to the x at this point. Both e to the x at this point and the parabolic graph at this point have concave up behavior, right? And that is what we're obtaining by adding this extra term into our approximation. All right, so let me go back to our notes as we saw them and continue on here. Now those are linear and quadratic approximations. Let's consider doing a cubic now. In general, right, letting t sub 3 of x be a cubic approximation of our function near x equal to a, right, then what we're going to end up developing for t sub 3 of x is going to be this calculation. You'll notice the first 3 terms, right, are the same as what we saw in the cubic or the parabolic approximation of f of x near x equal to a. What we add on to that quadratic approximation is this third term to make it a cubic approximation. Right? And what we are doing now is obtaining a graph not only where the slope is going to match the slope of f near a, and the concavity is going to match the slope of f near a, but what we might call the rate of change in the concavity for both t sub 3 of x and f of x is going to be similar at x equal to a. Right? And notice the pattern here, folks. There is a bit of a pattern being established, right? We do have this pattern being established here, right? Notice we are adding on a term that looks very similar to this term that we added onto the quadratic, except it's now 1 over 3 factorial instead of 2. It is going to be multiplied by f's third derivative at a, and then multiplied by the quantity x minus a raised to the third power. There is a pattern happening here, right? If I wanted to go back to and actually show that pattern in a little bit more explicit format, right? We might come down here below and just take note. I should have probably added that on at the beginning here, right? What we have going on up here is we do have the quantity 1 over 1 factorial times f prime at a times x minus a raised to the first power. We don't typically see those values, though, because 1 factorial is just 1, right? The number of ways to arrange one item, one way, right? Excuse me. So this denominator simplifies to the value of 1. 1 divided by 1 is just 1, so this leading value here, this leading coefficient, we're careful there, this coefficient on this term is just the value of 1, so we don't see it. And this power, anything to the first power, is just itself. So we don't typically see that power of 1 there. Right? Now here we also see that pattern. This is technically 1 over 0 factorial times f's, what we would say is 0th derivative. Right? We don't really have a prime symbol for that. How we handle indicating not taking the derivative of a function, having the 0th derivative, well, we just state the function, right? So that's why we just see this function stated above. But then that is times by the quantity x minus a raised to what power do you think? Well, that would be to the 0 power here, folks. And what is anything to the 0 power? Well, it's just the value of 1. So really here we have just f of a left behind. You go, well, what about 1 over 0 factorial? 0 factorial is also equivalent to 1. Again, we go back to our understanding there. How many ways can we arrange 0 items? There is one way that you can present nothing, right? There's one way that you could present an arrangement of 0 items. So the answer there is actually 1. So 1 divided by 1 again becomes 1. We have a 1 out in front. F's 0 derivative at a is just f times this quantity raised to the 0 power. Well, any quantity raised to the 0 power is also just the value of 1. So the very first term is just f at 1. Or, sorry, f of a, right? F at a, right? So there is a pattern here, right? An underlying pattern here that we are developing and following here, folks. All right? Now, if I bring our specific example into play, let's see here. I have a little sticky line. Let me get rid of the sticky line. Ooh, how am I going to do that here? Actually, I'm going to grab it right there. There we go. Okay. So for f of x equal to e to the x near x equal to 0, since f prime of x equals e to the x, f double prime of x equals e to the x, and now the triple derivative of f with respect to x is equal to e to the x, we're able to set up this as our cubic approximation of our function. You'll notice now the first 3 terms match our quadratic approximation, where we're just adding on now this 4th term. It is 1 over 3 factorial, right, times f's third derivative at a, where a is 0, times this quantity x minus 0 raised to the third power. All right? If we think about those values, first of all, how many ways can we arrange 3 items? Well, to calculate 3 factorial, it's just 3 times 2 times 1. Well, 3 times 2 times 1, that's 6. All right? F's triple derivative at 0 is just like the value of f's second and first derivative. It's just the value of 1. So this middle factor will turn into 1. And then times x minus 0 raised to the third power, well, that's just x cubed. So this fourth term we add on to this approximation is just 1/6 times x to the third power, or 1/6 x cubed. And down here we have this cubic approximation. And what you will notice, folks, it's a polynomial form. It's a cubic polynomial. It's a third degree polynomial. All right? And as I had highlighted in the second degree polynomial, the quadratic case, is that in a lot of cases, or in really any case, all this involves is a little addition, subtraction, multiplication, and or division. Right? We could very likely evaluate this, right, using some fundamental arithmetic. And what we'll see when we do is that we're going to get a rather precise approximation of e to the x near that value of 0. All right? If we think about performing that approximation, that is going to be 1 plus 1/10 times, we decided here this is going to be 1/200th. We really just have to add on this third term. Now 1/10 cubed is 1/1000th, times 1/6 is going to be 1/6000th. All right? So for e to the x, all right, equal to, well, so for f of x equal to e to the x, f is 0.1, or e to the 0.1 can be now approximated using this third degree polynomial approximation. And that third degree polynomial approximation is just going to be given by this bit of arithmetic here. As we said, it's going to be 1 plus 1/10 plus 1/200th plus 1/6000th. And that's the math we see down below here. And if you did common denominators, you could get a rational description of that approximation, which would be 6,631 over 6,000, where if you approximate that out as a decimal to several decimal places, you will get 1.10517 in value. All right? And if we compare that to what we had for e to the x, all right, you might note that is a rather good approximation. Comparing t sub 3 as 0.1 or 1.10517 to this value given down below here, 1.10517091808, we have an accurate approximation out to the nearest 10th, 100th, 1000th, 10,000th, 100,000th, and notice if we would round to the nearest millionth, this would round up to just 1 in value, and we really only have a difference of about 1/millionth in value. The difference here is just a few millionths of a decimal, if not just a few 10 millionths of a decimal in value. Right? I think millions is the fairer way of saying that. All right? So we get a rather accurate approximation of e to the 0.1 value, and we were very likely to be able to do it with just some paper and pencil methods, right? And or a little mental math, right? With a little addition, subtraction, multiplication, and or division, we can come up with a rather accurate approximation of this transcendental value. All right? Also note how the graphs behave. If we pull the graph into picture, you can almost not distinguish the two graphs from each other, right? Near this value of x equal to 0. They are almost right on top of each other in the scale of these graphs. If we compare these to the other two graphs above, we have certainly increased the accuracy of our approximation considerably. All right? So, folks, again, here what we just looked at, and this is to help facilitate this understanding of Taylor polynomials, what we call linear, quadratic, and cubic approximations of a function. Right? And we looked at it in a very specific case. And what we were using here was calculus, right? We were using the application of the limits in the form of derivatives to help us develop these calculations, right? What we go on to note, though, is that these calculations, right, in the above introduction, the approximation functions t sub 1 of x, t sub 2 of x, and t sub 3 of x, these cases for the linear, quadratic, and cubic approximations were all examples of what we call nth degree Taylor polynomials for a function. All right? They were all defining what we call nth degree Taylor polynomials. This being what we call a first degree, this being what we call a second degree, this being what we call a third degree Taylor polynomial. The degree of the Taylor polynomial matching the degree of the polynomial function. We are really just looking at a polynomial here as an approximation, but it's more specifically known as a Taylor polynomial due to its construction. All right? If we actually define what it means to be a Taylor polynomial, we see that given as follows. Here's the definition. It does present itself with this rather, what we might say is long form. Let me go ahead and shrink this down a little bit so it fits a little nicer on the page here. Right? It is this value t sub n of x equal to this pattern here, where, notice, right, the first four terms in that pattern describe the 0 degree Taylor polynomial, f of a, the first degree Taylor polynomial that we saw above, the second degree Taylor polynomial that we saw above, and the third degree. For an nth degree Taylor polynomial, that pattern continues, ... all the way out until we're using, right, the value of n in our term, where we're using the nth derivative of f, evaluated at a, divided by n factorial, times this quantity x minus a raised to the nth power. Right? Taylor polynomials are following this established pattern. Now, we can say that a little bit more concisely as follows. I might say here, alternatively, we can get this a bit more concise description of that. What we notice is a Taylor polynomial, t sub n of x, is really just a finite series calculation. All right? It's this finite series, or what we might see as what we might call sequence of partial or a summation up through the nth term, where t sub n of x we might think of as the sum of the first n terms in some other infinite series, right, given by this format here. This format, right, being the summation that starts from k equal to 0 and continues up to n being the degree of our polynomial, the degree of the Taylor here, times this argument, right? Or, well, I should say here, for this argument of the series. Here, this is the argument of our series. It is this constant with respect to k times this factor x minus a raised to the kth power, right? Where this constant with respect to k, this c sub k, this really what we might say is a coefficient, that c actually stands for a coefficient of k, is given by this factor here. It is f's kth derivative at a, all divided by k factorial. All right? We could, in fact, have those all combined in one. Let me maybe put that right here, where we have this and this. Let's copy that, replacing that. All right? We could also think of it as this quantity, this summation here. A little more compactly, though, we could think of it as this, where c sub k is equal to this. All right? What we do point out is it does appear to be the sum of the first n terms in what could be an infinite series. And you might start to guess what that infinite series would be. And if you guess Taylor series, a Taylor series, you might be on the right track there, folks. All right? Let's look at an example. Let's look at another example. We've really already looked at one example in the introduction here. Let's look at another. All right? Let's look at this case. In this case, we're considering approximating f of 3.9 for our function f of x equals the square root of x. All right? Now, the square root of 4 we are familiar with, right? The square root of 4 is the value of 2. As for the value of the square root of 3.9, all we really can start to say maybe is that it's certainly less than 2. Without just trial and error, without some sort of technique, coming up with an actual good approximation of f at 3.9, some approximation that has some precision out to several decimal places, could take some rigor, folks, if we don't apply some calculus in the process. All right? And what we might do is, let's consider doing this. This can be done using an n equal to third degree Taylor polynomial. All right? Again, that's going to be denoted as t sub 3 of x for our function y equals f of x equal to the square root of x, right, centered at this value of x equal to 4. And I don't know if I made note of that here. The value that we're near is where we say that this Taylor polynomial is centered, right? These polynomial approximations center themselves, right, around this value of x where we're considering developing the approximation. The precision decreases as we move away from that center, right? So that is what we see given here in the terminology, right? We're going to develop a t sub 3 of x for f of x equals the square root of x, right, centered at x equal to 4, or what we might say is near the value of x equal to 4. All right? Now, this is going to involve, if we think about the calculation, in this case, t sub 3 of x, if we go to the formula above, is going to be f at 4 plus f prime at 4 times x minus 4, plus 1 over 2 factorial times f second derivative at 4 times x minus 4 squared, plus 1 over 3 factorial times f's triple derivative at 4 times the quantity x minus 4 cubed. Now here's where a little bit of rigor is involved. You are going to have to calculate the first, second, and third derivatives for this square root function. And unlike the e to the x function, these are take a little bit more thought to get through their calculation. Keep in mind, though, the square root of x, following a power rule, does give us 1 over 2 root x, where if I follow the power rule now for that x, using this constant of 1/2, and x would be raised to the negative 1/2 power, f's second derivative would be negative 1 over 4 times x to the 3/2 power, where x to the 3/2 power is x times the square root of x, and f's triple derivative would be given by 3 over 8 times an x to the 5/2 power, where when simplified becomes x squared square root of x. Once I find these first 3 derivatives used in my calculation here, I'm just going to go ahead and evaluate them at this location where I'm centered. So f of 4, f prime of 4, f double prime of 4, and f triple prime of 4. I can evaluate all those at 4. And with a little arithmetic, right, I can obtain 2, 1/4, negative 1/32, and 3/56 from those values. If I take those values now and go back into my Taylor polynomial, the third degree Taylor polynomial, substituting those in, I will obtain this form here. All right? It would be 2 plus 1/4 times x minus 4 plus 1/2. Remember, that is 1 over 2 factorial times negative 1/32 times x minus 4 squared plus 1/6. Remember, 1/6 is 1 over 3 factorial times f's triple derivative at 4 times x minus 4 cubed. Simplifying these products of these constants, folks, I do get 2 plus 1/4 times x minus 4 minus 1/64 times x minus 4 squared plus 1/512 times x minus 4 cubed. Now, I will tell you, folks, you might be tempted to expand these higher powers of x minus 4, this quantity x minus 4, raised to these higher powers. You might be tempted to expand those values. I do want to warn you against expanding those. You really will just be burning time in the question, folks. Leaving these in this power form is going to work just fine. Because keep in mind, what we are going to do is we're just going to evaluate this now at our value of x. We're just going to come back and plug in 3.9 here, which means plugging it in here, here, and here, which when we take 3.9 minus 4, it gives us the same result every time, which is negative 1/10. We get a negative 1/10 here, a negative 1/10 here, and a negative 1/10 here, which arithmetically you can calculate pretty quickly with some arithmetic, right? You can evaluate these very quickly without having to expand that, right? So as for approximating f at 3.9, the approximate value of the square root of 3.9, this approximation is given by this value here. And notice I just substituted in the 3.9 into our polynomial function in its unexpanded form. We note those are, like I said, going to be negative 1/10 in value, which we might set up this way, where you can do a little arithmetic. Yeah, this is going to be 2 minus 1/40th, right? This is going to be 1/100th, so this is going to be negative 1/6400th. And then this is going to be negative 1/1000th, so this is going to become negative 1/512,000th, right? Which is this result here that I can obtain with just a little bit of mental math, and then breaking out a pencil and paper and doing a little arithmetic here. I could get these over a like or a common denominator, right? Where if not, I can also approximate these out to several decimal places themselves in a division and add those up, right? In the end, either way, we can use this to develop this value, 1.97484180 in value. From this third degree Taylor polynomial, I can develop this approximation with just a little arithmetic for the value given by the square root of 3.9. If we actually look at the calculator's result for the square root of 3.9, this is what the calculator gives us. And notice the degree of accuracy here, folks. This Taylor polynomial, right, is accurate out to the nearest 10th, 100th, 1000th, 10,000th, millionth, 10 millionth in value. We only differ by about a couple of 100 millionths, right? Which is extremely precise. So folks, that is our first section from Chapter 7 where we introduced what is known as a Taylor polynomial. And if we go back up to that definition here, we can start to see that it's hinting to this series that we're going to come to know as a Taylor series. And what a Taylor series is what we call a power series, right? This is going to lead to a Taylor series, a series that's going to come about with having up here in the numerator, what am I doing here? The value of infinity as opposed to n, right? But what the Taylor series is what's more specifically known as a power series. And if we look at this alternative format here that I've highlighted, if I set that upper bound equal to infinity, in general, a series that looks like this is known as a power series. It's a series that is a bit more functional in its description. It involves this functional description involving x being this independent variable raised to some power, right? And this is what we're going to familiarize ourselves with, known as a power series. We're going to study that in the next section, take a look at some power series and some properties of power series, and then we're going to come back and look at this specific case of a power series that relates to this format known as a Taylor series, folks. What this section is just really an introduction to these ideas. The introduction to Taylors being these approximations, these polynomial approximations of some transcendental function and its values, and then leading us into the study of power series. So I hope these videos are helping you out, folks, and I hope you're hanging in there. If you need anything, you know how to get a hold of me. We should have another video out for you here shortly. I got to work on the notes for that, and we'll get that posted, folks. But other than that, I will see you next time. Take it easy.